Okay, welcome to the second video where we're going to do some math with Dalton's law. And this is the easier math problems. You'll see the problems are going to get more difficult on Thursday. Okay, so let's read these two problems. So a scuba tank contains oxygen with a pressure of 0.5 atmospheres and helium at a pressure of 85 millimeters of mercury. What is the total pressure of millimeters in millimeters of mercury in the tank? Okay, so we learned that the pressure total, okay, is equal to the pressure of one of the gases, which in this case is oxygen, plus the pressure of helium. And by the way, these are called partial pressures. So the partial pressure of oxygen plus the partial pressure of helium is equal to the total pressure. And the problem here, though, and of course I cause it to be more complicated, is that the pressures are in different units. So if they were in the same units, we could just add them and get the total pressure. Okay, but they want it in millimeters of mercury, so I gotta convert the atmospheres to millimeters of mercury, so put that over 1, and we should know that 1 atmosphere is equal to 760 torr, and if I get my calculator out, we'll see that this is equal to, atmospheres cancel, this is torr, so this is equal to 342 torr. Okay, and now we simply have to add and again, torr and millimeters of mercury are the same, so this is also millimeters of mercury. So now we're going to add them together, so this is the pressure of oxygen, that goes here, plus the pressure of the helium, which is that, and I need to get a calculator to add them. So 342 plus 855, and we get 1197 torr. Okay, so I mean, simply we're just applying the law that if you have two pressures of a gas, to get the total pressure, you add them. All right, let's go to the second problem. Okay, so for a deep dive, a scuba diver used an addition of helium and oxygen with a pressure of 8 atmospheres. So again, we have pressure total is equal to the pressure of O2 plus the pressure of helium. So that's the two things that are in here. In this case, we have the total pressure, right, is 8 atmospheres. And they're telling us that the partial pressure of oxygen is 1.68. Okay, well, we know that the total has to add up. If you add these two together, they have to add up to the total pressure. So this is simply, we need to subtract the pressure of oxygen, and this is algebra, to get the pressure of helium. Okay, so we have 8 minus 1.68. And we get 6.32 atmospheres as our total pressure in the end. Okay, now, you can also do this. This can get a little more complicated, okay? Because you can be asked to do this with the ideal gas law. Okay, you need to get into your head, okay, that the total number of gas what the gas is does not matter. All that matters is the number of moles of total gas particles, no matter what they are. So if you look in this problem, okay, they give us the grams of F2 and the grams of carbon dioxide. And I actually want you to change this to make the math nicer to that. I forgot the 0 when I was typing this in. So in order to find the pressure, which is what it wants, total pressure, we need to find the number of moles of both particles. Okay, so we have for F2, we have 19 grams of it. And the molar mass, if you remember, of F2, remember it's F2, is the molar mass of 1F is 19. And there are 2 of them, so 19 times 2 is 38. And if I did my math correctly, this is a half a mole. Okay. And then for carbon dioxide, right, the total mass is 88.02, because I messed up on the typing. And the molar mass of this is 4.01, so the total mass is 2 moles. Okay, now, okay, again, to find the pressure, it doesn't matter what the gas is, okay, you just need to know the total moles. So the total moles here is 2.5. Okay, so now what we can do is we can use the ideal gas law, PV equals nRT, okay, to find the pressure based on the fact that the total moles of gas, doesn't matter what they are 2.5. Okay, so our pressure is what we're trying to find. Our volume is 3 liters, and it's a rigid container. Our N is 2.5. I'm going to want the pressure in atmospheres, just because I like atmospheres better. So we'll use that R, and the temperature is 283. So now this is some simple algebra. Let me put the numbers in my calculator. 0.08206 times 283. And then we divide by 3. And we get the pressure is 19.4 atmospheres, I believe. There. Sig figs. Yep. This one should really be a decimal place. 2 sig figs. So we'll just say 19 atmospheres. That really should have a decimal there. There's no way you report a temperature with 1 sig fig. There. Okay, so again, the point is that it doesn't matter what the gas is, as long as you know the total molecules of total moles of gas particles, no matter what they are, the pressure is going to be the same. Okay, now, this is the part that gets a little bit like annoying. And again, it's not hard, it's just a little bit annoying. So let's look at it. So we have something called a mole fraction. Okay, and a mole fraction is simply if you have a mixture of gases. It's the number, so this is like, let's say this is the mole fraction for gas I. It's the number of moles of gas I divided by the total moles that are in the mixture. Okay, so we're going to use this. Okay, this mole fraction can be used to find the pressure of individual gases in a mixture if you know the total pressure. Okay, and it's given by a formula. Okay, so here's the formula. So the partial pressure of the gas that you're trying to find is equal to the mole fraction, which remember we just learned is moles of I over the total, times the total pressure. Okay, and we're going to do some examples of this, and then we'll be done. Okay, so it says on a humid day in the summer, the mole fraction of gaseous H2 is this. So that's going in for the mole fraction. So we're going to put it in there, 287. Okay, and the pressure total on this day, or the atmospheric pressure total on this day, is that. Okay, and they want to find the pressure due to the partial pressure due to water, which is PI. Okay, so we simply get out our calculator, and if we do this mass, we get which is blue as the Boeings. This is actually H2O, so the pressure of H2O, partial pressure of H2O. And then if we do that mass, the partial pressure of H2O is 0.0280 atmospheres. Okay, again, okay, if you know the mole fraction of a gas, okay, and you know the total pressure, okay, all you have to do is multiply them together, and then you get the pressure of just the thing, the partial pressure of the thing that you're trying to find. Okay, now this equation can be rearranged, and we're going to rearrange it in a second because you're going to have to use this in a question on the homework in the front for question 6. So let's look how we could rearrange. Okay, so I wrote some things down, and you might want to pause the video and write them down. So we're going to rearrange this equation. We're going to divide both sides by pressure total. Okay, so pressure total. And that gives us, and I'm just trying to make the colors the same, so P1, that's word is skipping, over pressure total. And then if what's left on this side now is the blue X. And remember, this is mole fraction. So it's moles of the thing you're looking at, so moles of I divided by the total moles. Okay. This equation is going to be really, really helpful. Okay. So I gave a situation where, let's say we have a mixture of gases, and one of the components is H2. Okay. The total pressure of the mixture, or the total pressure of the mixture of gases is 800. So that's the total. Okay. And then we have to go to find the pressure of H2, which is 400. Okay. And now the total moles there are 8. Okay. And we need to find just the moles of hydrogen in the mixture. So if you look at this, this is 1/2, so 0.5. And then if this is 0.5, this area, then the number of moles of hydrogen has to be 4. Okay, so this equation, or the rearrangement of this equation, can be used to find, if you have 3 of these things, if you have the pressure of just one of the components of the mixture, if you have the total pressure, or you have the moles of one of the gases, then you can find the total moles. Okay, but this equation, or this rearrangement of the equation, okay, is going to be useful for you to use, especially on question 6 in the homework. So again, just to reiterate, okay, if you have the total pressure and the pressure of one of the components of the mixture, and you have either the total moles or the moles of the one gas you're looking at, the mixture, you can find one of these in here if you have 3 of them. Okay, this rearrangement of the equation is going to be very, very, very important. Okay, so we have 2 more practice ones to do, and these are not that bad. So, okay, so what is the partial pressure of carbon dioxide in a container that holds 5 moles of CO2, 3 moles of N2, and 1 mole of H2, and has a total pressure of 1.05 atmospheres? So the first thing is you want to find the mole fraction of CO2. Okay, and if we look, the number of moles of CO2 that we have here is 5, and to get the total moles, we have to add up all the moles. So 5 plus 3 plus 1 is 9. And then if we do that in the calculator, which is not a nice number, unfortunately, we get 0.55555555556. Okay? Whatever. How many 5s, it doesn't matter. Okay? That's the mole fraction for carbon dioxide. Okay? Now, to find the partial pressure, or the pressure of carbon dioxide in that mixture, you just simply multiply it, like the equation on the equation on this slide showed us. So if we take the mole fraction and multiply it by the total, we'll get the pressure of just that gas in the mixture. So if we do that, so we have to multiply this by the total pressure, which is that, and we'll do that in our calculator, 1.05, and we need how many sig figs? 2 sig figs, so 0.58 atmospheres is the partial pressure due to carbon dioxide. So welcome to the last problem. I've been interrupted several times, which is okay. So again, whenever you're given grams of a gas, which we are here, with oxygen gas and nitrogen gas, it's good to find moles. So I'm just going to do this up here quickly. Oxygen gas, we know the molar mass of this is 32, so we know that that N, or the number of moles of O2, is 2. And then for nitrogen, nitrogen is 28.02, the molar mass of nitrogen. We divide that, and the moles of nitrogen are 3. Okay, so again, we know that the pressure total, okay, is equal to the pressure of N2 plus the pressure of O2. Okay, so now what we can do is that we're going to write a mole fraction, and it wants the partial pressure of oxygen, right? So the total moles, mole fraction, right, is the total moles of oxygen, which is 2, okay, divided by the total moles in the entire container. 2 plus 3 is 5. And if we do that math out, which my brain is not thinking right now because I'm rushing a little bit, this is 0.4. That's the mole fraction of O2. Okay? And again, to find the pressure of oxygen, okay, we just take the total pressure, which is 800, and multiply it by the mole fraction. Okay? So 800 times 0.4 is 324. Which is the partial pressure of oxygen. Now this question, you're done at this point with this question. Okay, but just to show you, so if this is 320, and we know the total pressure is 800, then it's simple math, a simple subtraction, 800 minus 32, 320, sorry, not 32, to find the partial pressure of nitrogen. But again, okay, and again, the multiple choice loves these type of questions. Again, if you need to find the partial pressure of a gas, you find its mole fraction, okay, and just multiply it by the total pressure. All right, go do the practice problems. Have a good day.